Okay, hey guys. So this is the one you've all been waiting for. This is the kinetic theory derivation in slow motion. So basically I'm going to just go through that derivation again a bit more slowly and try and explain all of the steps so that you can follow in your own time and get hold of this. Because this is really big and this came up last year and I think you need to know it and need to know how to do this. So the first thing we start off with, we need to make some assumptions. They are 1, 2 and 3. The first assumption is that we're going to assume that particles do not interact with each other. And if you remember, I called them ghost particles. And we can say that they don't interact because, for one, they're so small compared to the volume that they take up in this box. And for two, we're going to assume, have no charge. They're atoms and molecules, neutral charge. So even if they do get close, the only way that they can interact is through van der Waals, which is really short range, really weak. So that's the first assumption we're going to make. The second assumption we're going to make is that this, whenever there are collisions with walls or anything, that they're going to be perfectly elastic collisions. Physicist can't spell, shocker. So what that's saying is that particles, if they bounce off the sides of the walls, they don't lose any energy. So in theory, I could start off with my gas at a temperature T and it would carry on at that temperature forever. No energy is being lost from this system. And the third and final one is that particles have speeds that are governed by a statistical or random distribution. So particles have a random distribution of speeds. So actually, in more detail, well, I'll talk about this a little bit later on, but basically we're saying that every particle in this gas isn't going to have the same speed, but some random distribution which will be governed by the Maxwell-Boltzmann curve, which we'll study a bit more next week. So there are our starting points. So the whole point of doing this really was that last week we had this equation, the ideal gas equation. By the way, these are our 3 rules for all ideal gases. And last week we had the equation PV equals NKBT. And that's fine. But the problem with this is that, as I said, all the parameters in this equation are for bulk properties. Okay, so the pressure of the whole gas, the volume of the whole gas, the number of particles in the whole gas, K is obviously constant, and the temperature of the whole gas. We want to rewrite this in terms of statistical single particle parameters, so then we can do more interesting things. That's the whole point of what we're doing here. So, okay, let's get started. So the first step really is we want to talk about pressure, really. Pressure is going to be our way in, so we're looking at basically doing this left-hand side of this equation. And the way that we do that is that pressure, we know, is equal to force over area. And we know also that force is equal to the rate of change of momentum in a given time. So before we get started, really that's the thing we want to be thinking of. We want to attack it through these 2 equations. So I'm going to start off by looking at momentum. So we've got our particle here. We're going to start off by assuming that our gas is made of 1 particle. It's got 1 speed v, and is moving initially in the direction left to right. So it's just collided with the left-hand wall. And sometime later we'll collide with the right-hand wall before bouncing back completely elastically. So it's going to come back, and we're going to wait until it's right back
where it was at the end. So I'm just going to delete this. So this particle has a mass m. I'm just going to get rid of this and move this over a little bit. So when our particle returns this wall, it's undergone a completely elastic collision. So its velocity now is going to be equal and opposite. It's going to be in this direction. So let's look at that then mathematically. So my change in momentum, delta p, is going to be mv before minus mv after. And I know you mechanics guys, you use u and v, that's fine. I'm just going to use something generic here, just call them both v, just makes it a bit simpler. So before mv is just mv, and after it's travelling in the opposite direction with the same magnitude of velocity, so that's minus mv, and that obviously gives us that the change in momentum is equal to 2mv. So I'm going to call that equation 1. We're going to come back to this a little bit later. Okay, cool. So we've got our change in momentum. So to calculate force, we need to know the change in time. Well, we can figure that out as well. Our time is just going to be the distance it's travelled divided by the velocity that it's travelled at. So that's going to be d over v. And it's travelled from here, from the left-hand wall to the right-hand wall and back. And this side of my box has dimensions or length x. So it's just going to be that. So let's call that equation 2. That's my time that it takes all of this to happen. Now we can sub that in down here. And we now know through an extension of Newton 2, essentially, force is equal to delta P over delta T, and in this case that's going to be 2mv from equation 1 divided by 2x over v from equation 2. And if I cancel some of that down, so my 2 here cancels with this 2, and if I multiply the top and bottom of this main fraction by v, it will cancel this v here and leave me with a square on top, so that's mv squared over x. That's my force. And actually that should make sense, because if I bring this x across here, what I've actually got is fx, which is a force times a distance, so you should be thinking that that will have units of joules, which makes sense because I've got an mv squared over here, and that should remind us of vk. So we're on the right track. Anyway, but that's just a side note. Okay, so we've got the force. Now what we can do is attack the pressure. So I'm going to call this new one equation 3. So F is equal to mv squared over x, and that's my equation 3. So pressure now. Pressure, as we've got up here, is just equal to F over A. So let's think about this. In fact, let me move this back over here and do a doodle. So pressure is the force over the area. So in the time that this particle has gone to the right hand wall and back, it's only had a collision with this wall here, so I can draw that, and it looks something like this. So what it's done essentially is, this is my right hand wall, RHW, and we know there's been some force applied from the collision of the particle, call that F, and hang on, we also know that this right hand wall has dimensions of not x, y, z, so we can say that this has area equal to yz. Okay, let's do this then. So our pressure then is just equal to my force from equation 3, so that's mv squared over x divided by my area, which is yz, and that's going to give me, well, I'm dividing by my x on the top, so that just drops down to the bottom, More algebraically, what I could do is multiply the top and bottom of this fraction by x. It would cancel on the top and leave it on the denominator. And that'll give me mv squared over xyz. xyz, well, let's have a look at this again. xyz are the dimensions of my box. So actually what we've got here is this box has a volume equal to xyz. We've just not really explicitly mentioned that yet. So that's that there. So I can substitute that in. Let's do that. So that gives us therefore that my pressure is equal to mv squared over volume big V. So another equation, let's call that equation 4. See how easy this is. It just rolls off the tongue. It all makes perfect sense. So let's just have a quick stop and a check. We now have, if I rearrange this, we've got PV, big V, equal to mv squared. We know that mv squared is something like particle energy, something like that. And on the left hand side we've got PV, which is reminding us of these guys up here. So we must be on the right track. And if you remember back, we talked about there was a reason why we put our constant next to T, and that's because kBT has a relation to energy. So we're doing something right. We've got PV on the left, like up there, and we've got something that's reminding us of energy on the right hand side. Okay, so we're doing something right. That's good. So I'm just going to get rid of that and just go back to equation 4. Now what we need to do is we need to start considering our initial setup. So we'll just paste our box in again here. We've considered really a pretty special case. We've got one particle in this box and it's only travelling in the x direction out of our xyz. So what we need to do is we need to start removing some of these problems, and the first thing we can do is we can say, instead of one particle, that's boring, we want lots of particles in our box. We want any number of particles, something arbitrary that we can use for any problem. So why not just say, instead of that, we've got n particles, so we're going to go from one particle to n. Now, all of these particles are still all travelling left to right, boring, same speed for now. But what happens when we multiply up, when we've got more particles? Well, you'll remember the amounts law. The amounts law said something like pressure is proportional to n. So basically what I'm going to do over here is I'm going to apply the amounts law to our box, and therefore to our pressure. So because these two things are proportional, if I increase my number of particles by n, essentially what I'm doing is I'm increasing my my pressure in the box by n as well. So this is going to become P is equal to n mv squared over big V. So we're not done there. I won't call that a new equation. There's nothing new there. So all we've done is we've took applied the amounts law, which we've looked at. So that's fine. The second thing we can do is we can remove this restraint where all of our particles are boring and travelling in the left to right direction. Currently, this box has 1 degree of freedom. So that's a degree of freedom. Basically, what that's saying is that our particles are currently restricted to only move in one dimension. That's boring and it's unrealistic. So what we actually want to do is we want to let this move in 3 dimensions. That's more realistic, so we're going to give it 3 degrees of freedom. So now instead of just colliding off one pair of walls, so it was just colliding here and here, it's now going to be colliding with 3 pairs of walls. So what we're actually doing is, if you think about it, we're now going to apply the fact that pressure is inversely proportional to area. There's now essentially 3 times, it's not strictly area, it's more to do with the number of dimensions that we're working in, but you can think about it as an analogy as the number, the area that the pressure is applied over. Now there's 2 extra pairs of walls, so it's a factor of 3. Therefore, my pressure is going to reduce by a third. So now we've got a third, try and write that a bit neater, a third nv squared over big V. Okay. But even though these can all move in different directions now, they're still all moving with the same velocity. They're still all governed by this one velocity v, okay, which isn't good. So the final thing we're going to do is we're going to go from one speed to a distribution. And actually what that actually means is that we're going to go from v squared to the mean of c squared. And the mean of c squared, so what that's actually saying is this is the sum of all velocities squared divided by the number. This is purely statistical and it comes from the Maxwell-Boltzmann distribution, which we'll study later. But we're interested that this works statistically with the mean c squared, because we're talking about a v squared here. We have to do the mean of c squared, not the other way around. So you'd be tempted to talk about the mean of the velocities squared, but it doesn't quite work like that, and that's because of the equation of this line. It has some e to the power some stuff, which is a function of x squared. So that's where that comes in, or v squared I should say. So all we're doing now is we're going to swap our single velocity with this mean of the distributions of velocities. So that brings our final equation then, do it in bold, to p is equal to a third n mean c squared divided by our big V. So that was the final equation we came to. Really important. And actually we went one further there, and we looked at, well, if we look at this equation, if I just pull out some terms, I've got 3 terms that interest me here. I'm looking at these 3, n, m, and v. N, m, and volume, big V. Now if you think about that, if you look at it, this is the number of particles, this is the mass of one particle, and this is the total volume of gas. So let's look at this. The number of particles multiplied by the mass of one particle, well, that's equal to the total mass of our gas. So if I divide that by the volume of our gas, that's equal to the density of the gas, which is really, really useful. So actually what we can do, if I move all this over, get rid of this, shove it over here with our Boltzmann stuff, we can rewrite this as P is equal to 1 over 3 rho mean c squared. So that was the other form that we arrived at. So the reasoning behind that was we now have 2 equations. We have an equation here where our pressure is defined by particle level kinetic theory parameters, so the mass of a single particle
the average speed squared, or the average square speed of a distribution of particles, and here, so maybe we could use density if we have a mixture of gases where the mass isn't the same for every particle, or something like that. So it is interchangeable, and we will find this useful in questions, which I'll, I think, cover next week, because this is quite a long video. So there are two equations, and that is kinetic theory. So next up will be, I think I'll go back and just do a short video on random walks again, because there's a little bit that I wanted to clear up with that. Anyway, thank you very much. I'll see you later.